Final part of section 10.2, the most thrilling section of them all in Math 129. Okay, using the second derivative test to find relative extrema of a function f. Now, we've already talked about the first derivative test. The first derivative test did what for us? It found relative extrema. The second derivative test does exactly the same thing. It will help us find relative maximums and minimums. It does the same thing. The outcome is the same, but the process is different. And I need you to learn this process, okay? Got to be able to show me the work. So here are the steps. I'm going to go ahead and explain these steps by way of example, okay? So you can pause the video if you like, take a look at this, and then I'm going to show you how to do this, how to perform the second derivative test by way of two examples. All right, example number 1. Find the relative extrema, if any, of the given function. Use the second derivative test. If it says to use the second derivative test, you need to use the second derivative test. Here's the process. First, find the first derivative. First derivative is 6x squared plus 6x minus 12. Now, you're going to let the first derivative be equal to 0, and you're going to solve for x to come up with any critical numbers that exist. All right, you let the first derivative be equal to 0. Solve for x. You're determining any critical numbers that could possibly exist. And what I'm getting here is that we have two critical numbers. We have x equal to -2 or +1. Okay, now I'm not going to do a number line now. That's what we did in the first derivative test. First derivative test was a sign analysis on a number line. Second derivative test is different. Okay, here's what makes it different. We will now come up with the second derivative. The second derivative. So what's that going to be? Well, it's based on the first derivative. That's going to be 12x plus 6. Now what I'm going to do is plug in each of these critical numbers into the second derivative to determine the corresponding sign. This is now the second derivative test. I should have written it down earlier, but whatever. Second derivative test is happening right now. After you found the second derivative, you replace every x with any critical number that exists, and you determine the sign of the result here. So in this case, it's what? It's a -18, right? That's the value you get for f double prime of this critical number, -2. This is, of course, less than 0. If it's less than 0, you think sad face, concave downward. Well, think about a point here on the top of this arc. Maximum. Maximum. Therefore, f of -2, original function, f of -2 equaling what? Plug in a -2 everywhere you see an x. You may use your calculator to do that. Original function. Everywhere you see an x, replace with a -2 now. You get a 16. This is a relative maximum. All right. Continuing on with the second derivative test. What about f double prime of 1, our other critical number? Well, in this case, you get what? 12 times 1 plus 6 yields +18, which is greater than 0. Okay? Because it's greater than 0, you're thinking, happy face, with a little bump right down here at the bottom of the smile. This is a relative minimum. So therefore, f of 1 equals what? Well, I don't know. Plug in a 1 everywhere you see an x in the original function to get the corresponding minimum. And I'm getting -11. And there you go. For example, number 1. Excuse me. Let's move on to example number 2. Number 2, given function f of x equals the natural logarithm of x squared plus 1. Process is the same. Directions are the same. Second derivative test. We're going to use the second derivative test to come up with any relative extrema, maximums or minimums. So first step is to come up with the first derivative. What's the first derivative of this? Natural logarithm of something is the derivative of the inside, that's 2x, over the inside, which is x squared plus 1. All right, so do we have any critical numbers here? Well, are there any values x that would make the denominator be equal to 0? No is the answer to that question. Are there any x values that would make the numerator equal to 0? Yes is the answer to that question. And that single value would be 0. 0 is your only critical number in this situation. Okay, what do we do next? We figure out the second derivative. So second derivative based on this, I'm going to use the quotient rule, low, d high minus high, d low, low, low. All right, let's neaten this up a little bit. So I have what on top? I have 2x squared plus 2 minus what? 2x times 2x is 4x squared. Putting it all together would yield what? 2 minus 2x squared all over the quantity x squared plus 1 squared. There's my second derivative in a more simplified form. So now what do we do? We're not going to perform the second derivative test. Second derivative test means we're going to do what? We're going to plug in any critical number we got from the first derivative into the second derivative to see what our corresponding sign would be. So, wherever you see an x, you're replacing it with a 0. And we get what? We get 2 minus 0 over 1. So we get 2 as a result. F double prime of 0 is 2. This is greater than 0, meaning it's positive. If it's positive, you're thinking happy face. And happy face, well, on the bottom of this, there's a little bump. There is a minimum, right? It's the bottom of this smiley face. So therefore, at f of 0, go to the original function, f of 0, which would be what? The natural logarithm of 0 squared plus 1, which would be ln of 1, which is 0. At f of 0 equaling 0. You plug in a 0 here, you're going to get ln of 1, which is 0. Right here at this point, you have a relative minimum. Now, if you want, this is function notation, but of course, you know, it's at this ordered pair. You can write it as an ordered pair as well. All right, function notation versus ordered pair. That wraps up section 10.2. That was a good section. A lot going on. It is tough. Hang in there, put the effort in. Reach out to me if you have questions or concerns.